let me narrate it for people who are so can everybody hear me? Only UI is there and all other things are remaining 0. So similarly, we can show that by developing all these things, the K matrix for this element is given by Ke by L C square Cs minus C square minus Cs S similarly minus C square minus Cs plus C square plus Cs and minus Cs minus S square plus S plus S square, where C is cos theta and S is sin theta. Okay, based on this, we have started solving a generic problem. For example, we tried to solve this problem and here a roller support, and we showed that anyway. Let me node 1, node 2, node 3, node 4, node 5, and this is element 1, element 2, element 3, element 4, element 5, element 6, and element 7. So, and our degrees of freedom were u1, v1, u2, v2, u3, v4, u5, v5. That is, we had 10 degrees of freedom. Those are, this is u1 is first degree of freedom, this is v second degree of freedom, third, fourth, fifth, sixth, seventh, eighth, 9, 10. So that means our global stiffness matrix was 10 by 10 by 10. So our global stiffness matrix Kg, which is a global stiffness matrix, was a 10 cross 10 matrix because we had 10 degrees of freedom. So, and our total degrees of freedom were D, which is 60, 78, and is singular because boundary conditions has been not given, and the boundary conditions has to be making the structure stable. That is, it should arrest all the corresponding rigid body displacement it has having. So when it arrested, then only you can invert the K matrix. So for that, what we did was, as earlier, we split this into KUU, KUK, KKU, KKK times our degrees of freedom. Our D is nothing but U1, V1, U2, V2, so on, U5, V5. Or you can write it as D1, D2, D3, D4, so on, D10, which is same as this thing, D1, D2, D3. So you can as well as write it as D1, D2, D3, so on, like that. So out of this, in our case, u1 is equals to 0 and v1 is equals to 0, since this is a pin support and since this is a roller support, v3 is equals to 0. So our known degrees of freedom, d known degrees of freedom, are d1, d2 and d6, because this is d6, this is d2 and this is d1. So then I can write it as d unknowns and d knowns, and d here d knowns, unknowns d3, d4, d5 and d7, d8, d9 and d10 is equals to corresponding f case are nothing but, if this d1, this would be f1, f2, f sorry, f6, and corresponding fu are f3, f4, f5, f7, f8, f9, f10. So I can write it as fu, fk. But we know that DUs is nothing but all are zeros, because u1 is 0, v1 is 0 and v3 is 0. So then we can write this into, anyway these are all 0, so this multiplied this is will be 0. Let me write it down for your convenience. Kuu into du plus kuk times dk is equals to fu. But since these are all zeros, this term will be neglected, and hence in the last class what I have solved is kuu du is equals to fu. We know the forces. Our FUs are nothing but, since we ignored self weight and the temperature variation, only external loads are there. With the external loads is nothing but, we have at fifth and sixth. So this would be Q4 and this is Q5. So this is nothing but F8. This is nothing but F8 and this is F10, which are equals to capital P. Sorry, minus P, because it is acting in the negative direction. Our X and Y directions are these things. This is X and this is Y. Since these are in the negative direction, it has to be taken as minus P. So this is 0, 0, 0, 0 minus P, 0 minus P was our forces due to external loads. So what we did is, to solve du, we have to do kuu inverse of fu. We know this, we know this. To get the capital Kg, rows and sixth rows and columns. The remaining thing would give you kuu. So once you get, that means you know kuu, you know fu, you get du. Now we will make use of the second equation from this. This is the first equation. This equation 1. Now equation 2 is this one. Equation 2, which is k k k k u into du plus k k k dk is equals to fk. What are these fk's? Fk's are reaction forces. We don't know reaction forces. We need to compute it. To compute it, we already know our dk's are all zeros, so this term is neglected. But from this, since using the equation 1 we already determined du, so once you solve this equation, bring it and substitute here, then when you multiply these two things, you will get fk, and that is how your reaction forces are computed. And we have showed it in the previous class with a greater detail how to do this procedure, and then we solved that problem on a notational form, but that math you can go ahead and finish it at a leisure time. I'll give you a suitable example using a MATLAB at a later point at the end of the chapter 3. So this completes the thing about the trusses. Now what we will do is, if you have any questions, I will take it. Otherwise, we will go to the second part of the chapter 3, which is beams. So in the beams, if you look at beams, in most of the civil engineering and mechanical engineering, you find beams, there are common usages, let's say in buildings, or you have gantry gutters and other things which rest on the beams that are running all around the corners and along the wall, so that that will take the loads from the cranes and distribute it to the columns at a later point. Let's take a typical beam. Beams can be of several types depending upon the boundary conditions. One is like this is a cantilever beam. Can be a fixed beam. That means both sides are fixed beam, or a simply supported beam. And there are other overhanging and other kind of things depending upon the boundary conditions. So having said that, this is the classification based on the boundary condition. There are also other classification based on the theory. Most popular thing that you might have already learned in your strength of material that we'll be discussing today is Bernoulli beam theory. Why we are studying Euler-Bernoulli beam theory today is, even before you solve a solution of a beam, you should know that how you are modeling this beam. Okay, the basic model of a beam is starting with Euler-Bernoulli beam. Okay, then there are Timoshenko beam, then first order shear theories, second order, and higher order theories are subsequently there. But Euler-Bernoulli theory is the most popular one and most basic thing. So the first, there are certain assumptions behind this. Assumptions is, first thing, plane sections. Plane sections means plane cross sections before the deformation remains, let me say, plane sections. Okay, it's fine. Plane sections remain plane, and we have to say plane sections which are perpendicular to neutral axis. Before the deformation remains plane and perpendicular even after the deformation. This is one of the basic important assumptions of Euler-Bernoulli beam. This is the first one. The second thing is, this is very quite common. What is neutral axis? Neutral axis is defined as our neutral plane and whose length remains. Anyway, the third one is not really an assumption, it's a consequence of the first one. But anyway, let's see that what does this assumptions make. Okay, so this third one is not yet complete. The beam is subjected to pure bending, and the beam deforms as a segment of a kind of circle. So that means, let us consider a beam let's consider a beam, whatever is the boundary condition, I'm not worried about it. But since I said it is under pure bending, so let me put it in this form. It's a pure bending. So under this kind of sagging, so what will have is it will bend. It will bend so this bends as actually this I should not have drawn it like this. Let me redraw it. It bends something this. So it bends as an arc of a segment. So if we extend this like this, then this is the center of the circle, and this would be the radius r. Okay, so and let us consider a neutral axis, the neutral axis, and this neutral axis even after the bending, it remains same in length, which runs through the center of the cross section. So this is neutral axis before deformation. This is neutral axis after the deformation. So the length of those things would remain the same, which is there in this, which is equal to the length of the beam is L. So, or let me call it as L naught. So this is the length of the neutral axis. Further, is equals to theta. Okay. Now, if that is theta, we know that an arc length S is equals to R times theta. Okay. So this is not the sine theta kind of things. An arc length. This is arc length or a segment of length is equals to radius times the angle inclination between the both the ends. Okay, so S is equals to R theta is the same thing. Now let's say from here to the center of the circle, from the neutral axis to the center of the circle, this distance is R. Okay, if that distance is R, and let us find out at a distance y from the neutral axis at a height. So this is your cross section. In cross section, further this is your neutral plane or neutral axis, and I want to see what is happening to a fiber at a distance y. So the fibers that are on the top of the neutral axis has shrunk in size, whereas the fibers that are below, so this is under the tension, that means elongated. The fibers that are above are under compression. So now I can write theta is equals to R by S. Okay, and okay, let me rewrite it. So you see that the length of this of the neutral axis since is L, I can rewrite it as R by L, whereas the same theta or L naught at a distance R. So let's consider a fiber which is at a height y. So for that one, let me say this is a fiber which is at a length y from the neutral axis. So the neutral axis is this fellow. So neutral axis is, this is the neutral axis, same as this is the neutral axis, and I want to see a fiber which is at a height y. So in the deformed configuration, this may be a fiber which is also deforming as arc of a segment at a height y from the neutral axis. Let's consider its length as L. So I can rewrite this as L by L naught is equals to R minus y by R. Or I can say that L by L naught minus 1 is equals to okay or L minus L naught by L naught is equals to minus Y by R. But what is the length of fiber purple color or this color before the deformation? In the before the deformation it was L naught. All the fibers were L naught. After the deformation it length was L. So L minus L naught is the change in length divided by original length. So it gives strain in the fiber. So epsilon is equals to L minus L naught by L naught, that is equals to minus Y by R. Okay. So we can write epsilon is equals to minus Y by R. This is an important result. Okay. Now what is the stress in the each fiber? The stress in the fiber is nothing but E times epsilon using linear elasticity, then that will make minus Ey by R. So now you can see that for the fibers which are above the neutral axis, since it is positive, since Y is positive, you'll get a compressive strength. When Y is below the neutral axis, Y is negative, negative times negative, you'll get positive. So below the neutral axis, this is under compression. That means along the cross section of the beam, let us assume some rectangular cross section for simplicity. It can be any shape of the cross section. We have shown that the stress or strain distribution is linear in terms of Y. Y is measured from the neutral axis. So with respect to Y, this is linear, and when Y is equals to 0, it is 0. So the stress or strain is linear in terms of Y. So this is compressive and this is tensile. Great. So this is one thing. And now using statics, we can show that if I take sum of all the forces along this thing, dy minus h by 2 to h by 2, let us say this is minus h by 2 and this is h by 2, the height is h. Anyways, these are the same triangles. One is there in the positive negative side and the positive side. The sum has to be equals to 0. So even without doing it, without substituting, I can clearly say that this is equals to 0. However, we take the same thing and do sigma y dy, then using the above term, I can write it as minus Ey by R into, let us also multiply the area. So once you multiply the area, what you'll get is equals to the moment. Okay, moment M y dy, that is equals to E by R by square, or you can write M by E is equals to ay square dy divided by R. But this term is nothing but your moment of inertia. So that means M by E is equals to I by R, or alternatively I can write M, put a minus sign here, But using calculus, one can show that R is equals to dx2 divided by 1 plus dy by dx whole square to the 3 by 2. This is approximated as d square y by dx2. Since this is small, its square is small, its very is negligible. When you make it to the power of 3 by 2, it can be neglected altogether with all these things. So I can write m by ei is equals to d square y by x2 equals to, because this is equals to d square y by dx2. Or one can show that d square y by dx2 ei is equals to m. So this is your governing differential equation coming from Euler-Bernoulli beam theory. Anyway, I didn't talk about the consequence of Euler-Bernoulli beam theory. The consequence of Euler-Bernoulli beam theory, the first one says that no shear stresses are present. Why? Because we know that before the cross section, before the deformations, this is the plane and this is the neutral axis. Whereas after the mission, the neutral axis was something like this, and the planes remain still plane. The planes still remain plane and perpendicular. That means perpendicular means will also remain 90 degrees. Relates with the shape changes will give you shear stresses, and there are no shape changes. Size changes will give you normal stresses. So we only have size changes. The one on the top has sizes changes, which is compressive in nature, so shrunk in length, and the fibers that are other side of the neutral axis has increased in as elongated and hence increased the size of those fibers. So anyway, so this is an important result, and we also showed that there is only one kind of a stress, which is normal stress, that we derived from the bending theory, pure bending and the Euler-Bernoulli beam assumptions, and then using the curvature and d square y by dx square definition, we have derived that ei d square y by dx2 is equals to m. But this is not complete. We have to do further. So let us use equilibrium equations. The equilibrium equations are, let us consider some kind of a beam, whatever it may be loaded. Some w of x is there, some point loads here and there, whatever is there. I will take a small cross section dx, and then I'll try to zoom in. When I try to zoom in, I'll get, let's suppose this is the zoomed cross section, which is dx. Let us say, let's consider the notation, the convention for the shear force and bending moments are anti-clockwise is plus m, clockwise is minus m. V that causes this rotation, this movement is positive. So that means this is causing clockwise. So okay, let me put it in the other way around. So this is okay. We can just remain it as it is. It doesn't hurt me doing. So let me call it as V. But this still this is the notation. So this is V. This is V plus dV. This is M, and this would be M plus dm. The notations are still the same. So, or you can choose one notation and keep continuing that notation all throughout. You have to be consistent with your notation. So we choose this as our notation. So if I take a force balance, is the weight that is acting on it. So V, let's say we are doing the vertical forces, V minus W of, let's say, simply call it as W into dx of V plus dV is equals to 0, or simply I can write W dx plus dV is equals to 0, or dV by dx is equals to minus W. The rate of change of shear force is equals to is equal to distributed load. Now similarly, let me take the moment balance. When I take the moment balance, it is positive, and the other one is M plus dm is in the negative. Next, my shear force is also creating. So anyway, this guy will not. Let me take a moment about this place. Let me take a moment about A. Let me call it as P. If I taking moment about it, this would not contribute. However, this would cause a clockwise movement. So next, plus W dx is the total load, and its moment is dx by 2. Since dx is small, dx square is much smaller, so I can ignore this. So then this fellow will go. Then I will have, sorry, this is a negative moment. This is a positive moment. Let me see. This is clockwise is positive, so this is positive. This is negative. This guy is again negative. This would be acting at the center in this. So negative. Sorry about mix up. Anyway, this term is not giving any significance. So I can write my dm by dx is equal to v, or simply telling it rate of change of bending moment is equal to shear force. Okay, now I make use of this equation 2, then I make use of this equation 1. I can write from 1 and 3 dm by dx is equals to d by dx of ei d by dx square. Similarly, this is equals to V, and further I take another dV by dx is equals to W, that is equals to d square m by dx square, that is equals to d2 dx2 ei d square y by, this is with the minus sign, dx2. So that means my ei d square y by dx2 d by dx2 is equals to minus w is my governing differential equation. When E and I, that is E is homogeneous and I is, that is cross section is prismatic, then I will not change. Homogeneous E is not a function of x, E is constant, I is constant. What happens is I can take EI out, EI d4y by dx4 is equals to minus w. The boundary conditions can be anything, but yeah, when you are showing it w of x, this E and I and the length L, you can show that the governing differential equation for the beam is governing differential equation for an Euler-Bernoulli beam. So this is the governing differential equation for the Euler-Bernoulli beam. So if you have any questions, please let me know, because this governing differential is important for us to solve in the subsequent things in the finite element sense. At this given point, I will stop and I will check if you have any questions. This is fourth order linear ordinary differential equation. Okay, so this fourth order on ordinary differential equation, if you have to solve it, then you need what? We need at least 4 boundary conditions. Okay, so what would be the boundary conditions? You can mention either y, or you can mention dy by dx, or you can mention d square y by dx, or you can mention t cube y by dx. Multiply respect to ei, then this would become em. If I multiply ei, then this would become v. So and y is the transverse deflection, and dy by dx is theta. So that means either you can mention y, you can mention slope, you can mention bending moment, or you can mention shear force. So these things, because it is fourth order differential equation, so you can mention any of these things in any order. However, if you are mentioning only y or dy by dx, anyway, let us, what is the order of differential equation? It is 4. So if n is the order of thing, the first 0 to n by 2 minus 1 differential, if you try to mention it, those are called kinematic boundary conditions, or also known as displacement boundary conditions, or Dirichlet boundary conditions. And anything the derivatives from n by 2 to n minus 1 you mention, those are called natural boundary conditions, or force boundary conditions, or Neumann boundary conditions. So let me see. What is the power? What is the differentiation of this? It is 0. That is only the function. So 0 for in here n is equals to 4. So y, and what is 2 by 2 minus 1? 1. So y 1 or y dash are your kinematic boundary conditions. So if you mention y, or this is also called as y dash, so these kinematic boundary conditions. These are kinematic boundary conditions. If you mention any of this bending moment or shear force or any other combinations of it, then it is called natural boundary conditions. Okay. For example, let us see a with a point load at the tip. Okay. If you try to do this thing, then the boundary conditions are y is equals to 0 at x is equals to 0 and theta is equals to 0 at x is equals to 0. Now if at the other end, let's the length of the beam is L, then it is d cube y by dx cube. EI is the shear force. At this point, the shear force is equals to the given point load P. Similarly, EI d square y by dx square, which is nothing but bending moment. There is no bending moment. There is no moment applied at this point. So this is the thing. So there are fourth order has 4 boundary conditions. If you take, let's say, a fixed beam. So what are the boundary conditions? Let's say x is measured from here, y is equals to 0 and theta is equals to 0 at x is equals to 0 and y is equals to 0, theta is equals to 0 at x is equals to L. These are the boundary conditions for a fixed beam. Now for a simply supported beam, now here when it sags, you know the slope is not 0 but the displacement is 0. So y is equals to 0 but theta is not 0. If theta is not 0, its conjugate has to become 0. The conjugate of theta is moment, because the hinge or the pin joint cannot take any moment. M is equals to 0 at this. M is 0 is nothing but EI d square y by dx square at x is equals to 0 is equals to 0. Similarly, y is equals to 0 and m is equals to 0 at x is equals to L. So these are the some of the examples of the boundary conditions for the beam. So now what we need to do is, this is governing differential equation plus boundary condition gives you a boundary value problem. Okay, and this boundary value problem, not always you have a closed form analytical solution. So maybe these are very simple equations, so you may get it, but in 2-dimensional and 3-dimensional, this would be plate and shell, plates and block elements and other kind of things, solid elements, solids. So generally having a solution, analytical solution for a partial differential equation is very difficult. So we will demonstrate with respect to a one-dimensional beam that and uh, and then you also compare it with the analytical solution. So what I will do is, first I'll try to solve the deflection of a simple cantilever beam with kind of a point load or a distributed load analytically, and then show that how the same thing can be used to kind of generate a solution using approximate methods. That is, approximate methods is how to obtain the solution using finite element method for the beams. So let us see an analytical solution. For example, first example, the simple thing you might have already done n number of times in your life. So let me measure x from here. So y is equals to 0 and theta is equals to 0. Theta is nothing but dy by dx is 0 at x is equals to 0, and this is p minus, and so I can either we can solve this thing using EI, but this means I need to integrate it 4 times. But anyway, the thing I want to convey it from here is, so any solution y you are getting it analytically has 4 requirements. That is, y has to be continuous, dy by dx has to be defined, and it has to be continuous. So that's the reason d square y by dx square has to be able to be, it should able to have d square y by dx, and it has all differentiable. So continuous and that means it is, if it is only y and it is continuous, it is c0. Analytical or an exact solution should be such that y should belong to, has to be y has to be continuous, dy by dx has to be continuous, dx3 has to be continuous, d4y by dx4 has to be continuous. Then only there is a solution for that given problem, provided it also satisfies the given boundary conditions. So that is the stringent requirements for having an analytical solution. At later point I will show that if you are seeking a finite element solution, let's say y tilde is an approximation, y tilde need not belong to C4. Y tilde even with a C2, I can get you a solution. That is the great of a finite element thing. But for now, let me not talk about these things. Let me keep it aside, because y tilde is an approximation. I'm not doing approximation in today's class. I'm only solving the exact solution today. So let me go ahead and solve these things. I can solve it in this manner, or I can do So this is m means m of x. I will start with this. At any given section x from the thing, since this is x, this would become L minus x. So the moment this place m of x is equals to b into L minus x with a negative sign because it is a clockwise movement. So d square y by dx square L minus x. Now I will try to integrate it. So d square y by, if I integrate it once, dy by dx ei is equals to minus plx plus bx square by 2 plus c1. Similarly, if I try to integrate it again, then it will become x square by 2 plus bx cube by 3 plus cx plus c2. So now how do you obtain this complete solution? If you have to get the arbitrary coefficient c1 and c2, then you need to substitute, or you need to use boundary conditions to determine c1 and c2. So let's try to do that one. We know that y is equals to 0 at x is equal to 0. So let me substitute the same thing in this statement. So this is 0 ei into 0 is equals to minus pl x square by 2 plus px cube by 3 plus c1x plus c2, everything defined x is equals to 0. At x is equals to 0, x square is 0. At x is 0. So ei into 0 is 0. 0 is equals to c1, or implies c1. Sorry, this is c2. I'm sorry about that. c2 0 is equals to c2. That implies c2 is equals to 0. That means this is gone. This is 0. We determined one thing. Now dy by dx is equals to 0 at x is equals to 0. That means I make use of this equation here. So ei into 0 is equals to minus plx plus px square by 2 plus c1 at x is equals to 0. At x is equals to 0, this is 0, this is 0. So my final equation eiy is equals to minus plx plus px square by 2, or y is equals to minus pl by, sorry, px by d by ei x into x by 2 minus l with a positive sign here. So this would be the deflection profile. So the solution y of x is p by ei x into x minus l by 2. So we know that the maximum deflection occurs at an x is equals to. So what I will do, I will substitute this y max occurs at x is equals to l. So I'm sorry about it. This I made a mistake. I'm sorry. Statement of I made a small error. So this is not y of x. Y of x is, I need to use this statement with c10, c20. I used this statement. I'm sorry about that. So this is, um, if I take x square common, I'm sorry about it. Square common and 6 common. This should become, I'm sorry about, somehow I took a wrong equation to determine. So 2x minus 3l. So now y max occurs at y at x is equals to l. Then when I substitute pi by l square by 6 to 2l minus 3l, that will give me, let me just see, let me see if I'm not making anything else wrong. um, I have made something wrong. So when I integrate it, this will become, already 2 is there. When I integrate it, this will become 6ei. So answer you might have also studied elsewhere. This will give you PL cube by 3ei with a negative sign because the deflection in the bottom side is considered as negative. This is how you elastic profile or elastic curve. This is your elastic curve, and this is your maximum deflection. Similarly, we can even do it for other modes, which I leave it as an exercise for you to do. Um, So that is how you easier problems you can get your analytical solution, and it is guaranteed that you can obtain it through simpler things. But once it becomes partial differential equation in 2D or 3D, then they cannot be that easily integrated. And even if it has a solution, and obtaining that solution for a complicated geometry becomes very difficult. In those scenarios, validity of the finite element, or to see how the finite element performs for the complicated scenarios, first you should also know how the finite element also performs for a simpler cases like beams of this nature. So that's the reason our next target is how to find how to find the solution of this thing using numerical approximation through finite element. So in order to do that, what I will do is I will start writing my governing differential equation, which is in the strong form, in the weak form. So let me rewrite it again. The strong form, or ODE form, or differential form of governing equations for a beam is d square by dx2 ei d square. This is your governing differential equation. Now let's do something, that is, let's consider instead of y tilde as an approximation for the exact solution. So that means it comes with an error, okay, which is, this is your approximation and this is the error that is involved between the exact solution. What I do is I try to take these things and substitute in the above equation. If I substitute in the above equation, then I would get d square by dx2 ei so it will leave some residue. So where r of x is the residue due to approximation in y, or that is by substitution of y tilde. So this r of x would be vanishing if it were the exact solution, but we know that we don't start with an exact solution, so it's just an approximation. So since it is just an approximation, we leave with the residue. Now what we do is we go back to our um, chapter 1, where we learned method of weighted residual, and we'll recall it. Okay, so let's recall the same thing and use it here. The method of weighted residual says that some weight should be equal to 0. This is what is called method of weighted residual. So what we do currently here is we will go with the Galerkin method, but even before I go with the Galerkin method, let me assume my V as weight, capital W, and my R here, it is easily defined as d square ei. So this is my residue. Now I make use of this thing and I substitute in here. 0 to length of the beam, weight is V, d square by dx square, ei, d square, dx2, dx. I need to equate it with the 0. Anyway, so sorry, there's another term. It is not totally the thing. I'm sorry about it. Plus w dx is equals to 0. This is also there. There is some w of x is still remaining. So this has to be the residue. So when I substitute that and integrate over the entire length, the total residue should vanish when I multiply with respect to v and integrate it. Okay. So let me call UV rule or integration by parts. The integration by parts says that integral v du is it equal to uv whatever is 0 to L minus of u dv, the integration of parts. Now I make use of this kind of things on the first term. So the first term of the above equation is 0 to L v d square by dx2 ei d2 by delta dx2 dx plus v w dx 0 to L. So what I do is, using the integration of parts, I would like to write it this one as 0 to L v d by dx of d by dx of ei d square y tilde by dx2 dx. And I call everything inside this, if I call it as u, then it is in v du. I can replace this term as 0 to L v, sorry, as integration by parts v times d by dx ei d square y tilde minus of 0 to L dv by of d by dx into d by dx of ei d square y tilde by dx2 dx. Okay, the same term has been elaborated. So this is the same term. I'm only expanding the first term. This is the first term. First term is this one. I rewrite in this form, which I call it as u, and then if I call it as v du by dx will become vu evaluated 0 to L, and then dv by dx into u dx. So again, what I do is on this use integration by parts again. By doing the integration by parts again, you will make, now I will rewrite dv by dx as d by dx of again ei d square y by dx2 dx. I call this guy as a new u. So, and this guy as a new v. If I call it in that manner by integration by parts, I can say that it will become v times u minus of minus plus d square. So this is the second term. So if I combinedly write it, the first term can be written as integral dv by dx ei d square y tilde by dx2 plus d square v by dx2 ei d square y tilde by dx2 dx. This is the first term. This is all this is entire the first term. But what is the second term? The second term is this one. Plus is equals to 0. This is second. So this together equation, first term and second term in this form, is called weak form. It's called weak form of the Euler-Bernoulli beam. Why it is weak form? Because if you take, we need to spend a couple of minutes with it. The thing is, now in order this thing has to have a solution, the y has to be only, y tilde has to be only differentiable twice, and it has to be also this d square y by dx square has to also be continuous, and these integrals should not give you, should be bounded. That means it should not give you infinity. So that means there is only special requirement that y belongs to C2. Not only that, v should belongs to H2. That means not only it is differentiable, but when I do some integration like this has to be finite. If it becomes infinite, then this integral term has no meaning, because infinite forms cannot be recovered. And these things, dv by dx and v and dv by dx should be 0 when y or dy by dx is specified. I think I have already talked about my best friend case in the previous solution. That means it is this virtual friend V has to be selfless and should not have ego. So that means you are like y and dy by dx, or you can even put whatever y tilde does, because at the boundaries your y and y tilde both agrees, so they are exact at the boundary. So it has, you can call it as y or dy by dx, they are same as corresponding y or dy by dx. So whenever these are specified on the boundaries, the corresponding v and dv by dx should go to 0. That brings another thing, that it has to be homogeneous. So this 0 requirement puts that v is, your weight is not just a normal function, it has to be C2. Not only that, it has to be, they have to be integrable, that is H2, and it should go 0 wherever it is, its corresponding y and dy by dx has been mentioned, and hence it is called, let me rewrite it here. So there is a special requirement that this should belongs to H2 0. This is the special best friend definition. You cannot choose any function as your weight, but there are special requirements to choose the weight. So this is the governing differential equation. This is still the governing differential equation, or governing equation. Governing then I can solve this problem. So to summarize what we have done today, what we have done is we have defined what is Euler-Bernoulli beam, developed its governing differential equations using Euler-Bernoulli beam assumption, that is plane sections remains plane and perpendicular. Then using statics we and the Euler-Bernoulli beam assumption, we finally derived the governing differential equation in its strong form. But we know that approximate methods doesn't like strong form. So what we did is we used a method of weighted residual, which we have learned in the chapter 1, and using integration by parts, we brought that into the weak form or integral form. Special requirements that are there on the on this beam structure, on this weak form, so that we can proceed in the further things. So at this point it is better to take a break and continue in the next lecture. At this point I would stop and check if you have any questions.